Okay, thank you everyone. My name is Matías Toro. I'm going to present this this work called Robust Dynamic Embedding for Gradual Typing. This is a joint work with Koen Jacobs, which is the first author, which couldn't be here, Nicolas, Tabareau, and also Éric Tanter. So to start, I want to give some context. I want to differentiate these two notions, syntactic typing, which we are accustomed of. We are used to it. We have static typing that uses this symbol like V' here, and we also have this notion of semantic typing that uses this model symbol right here, where semantic typings mean whatever semantic property we might want to hold. For instance, we might say that the expression E is semantically typed to tau if it reduces without errors to a value of that type. And usually what we do is we say, okay, static typing is going to imply semantic typing. So static typing is a over-approximation of the behavior of the expression. So now suppose you have a dynamically typed language. In a dynamically typed language, we have this program G, where in G we define this function f, which is a function that takes two arguments. The first one is a Boolean, or a b in this case, and the second one is an h, which is we're going to use it as a function, and then the body of the function is going to ask if b is true. Then we're going to apply h with 0 and this Boolean with true, and otherwise we are going to apply h with just one argument, which is 1, and then we are going to apply f to false, and of course this is a perfectly valid program, and in fact is semantically typed to this type. So given any semantically typed function from nat to nat, then we're always going to return a nat without errors, given that the function that we receive as argument is also semantically typed. So the question is, what happens if we try to statically type this program? This program, we cannot statically type it because H could have like either two types, either like a function that takes a nat to nat H is either a nat to nat function, or nat give me a nat, give me a Boolean, and give me a nat, and I'll give you a nat function. So so this cannot be statically typed. So one option is to use dependent types, or another option is to use gradual typing. So we can embed this dynamically typed language into a gradual type language by inserting unknown type annotations, mostly everywhere. So this is called the embedding. So we use this unknown annotation to represent any type. So in this case, the type of B is unknown, the type of H is unknown, and we also insert some unknown annotations in the boundaries between the static and dynamic parts of the code. So in this case, we insert a cast from 0 to unknown, and a cast from 1 to unknown. And so how gradually typed languages work? This program is optimistically accepted. Everything is fine because unknown is optimistically consistent with any other type. But this optimism must be backed up with runtime checks. So this program is going to be elaborated by inserting casts. So for instance, the argument B must be a Boolean, so it's going to cast to a Boolean. And the H is in the first application of H is also cast to a function, and so on. So these yellow ascriptions means either a cast or either an ascription or evidence or whatever you want. So if we apply, checks are inserted basically at the boundaries between terms of different precisions. So if a check fails, so in a gradual type language, then a runtime error is produced. So for instance, if we take f applied to 1, ascribed to unknown, cast to unknown, then this is going to reduce in many steps to 1, ascribed to nat, ascribed to question mark, ascribed to Boolean. And this, of course, these casts are going to be combined, and this is going to produce a runtime error. All right, so let's go back to what we start. So we have a dynamically typed program, and we know that it's semantically typed to this type. So what happens if we embed it into the into a gradual language? And not only embed it, but also how about if we assume or assert that this program is going to have some static type. So what happens if we take this embedding and we ascribe it to its semantic type? So what happened with this program in general? So now we have this program P where we have G prime, which is just the dynamic embedding of G, ascribed to its semantic type, which is give me a nat to nat function and I'll give you a nat. And then we apply it with some arbitrary H function, which can be gradual or static or whatever. So the question is P free of runtime errors? If the program throw a runtime error, then was it because of cast in G prime? Was it because of casts on H? Intuitively, we know that G is semantically typed to this static type. So morally, it should be the H should be the culprit of a runtime error. And if not, if G prime fails, or this program fails because of a cast in G prime, then maybe we are going to start doubting about if G is actually semantically typed to this type, right? So there are some expectations that we have because we know that this G is semantically typed to that type. So the first thing we did was check all the desirable criteria for gradual languages that is in the literature. There is a lot of properties. Of course, this is not like a mandatory list. These are desirable, so it's a criteria. So we're going to explore two of them that has to do with the dynamic embedding programs. So for the first one, the most close one is the dynamic embedding criterion by Siek here. So it says that if you have a dynamic expression and you embed it into the Gradual program, then this embedding has to be well typed and to the unknown type. And the second part, it says that if you have a dynamic expression that reduces to some value v, this happens if and only if the embedding of v also reduces to the embedding of v. So the reduction must behave the same. But it doesn't say anything about basically ascribe expressions and only reasons about closed expressions. The other property is the blame theorem that says that, informally that well-typed programs can be blamed. Basically, it's trying to blame always the imprecise type if you have a cast between two types. So to do that, you have a runtime checks that carry labels now that shows indicate the location of the cast, and they also have a polarity to know who to blame. And in particular, there is a corollary that says if you have a fully static type, then blame has to blame the context, right? In this case, it would be the blame of the context. So what happened with the previous program that we had before? So we have the embedding of G ascribed to this static type. So the blame theorem would indicate, as we have a cast here from unknown to this static type, then this program cannot fail while blaming the context. But it doesn't say anything about that it cannot blame by failing because of an ascription in G or a cast in G. Because this fact can only be derived by knowing that G is semantically typed, which is something that is not part of the property. So in this paper, we introduce a new criterion that we call the robust dynamic embedding, or RDE. And to present this, we start with first the definition of what it means to be robust. So we say that a gradual expression is robust for some type tau if its internal cast can never fail when used with any surrounded gradual code that use it at type tau. So intuitively, if you have an expression E, we say that it's robust at gamma and tau if given any context that is well typed for gamma and tau. With a hold, yes, and we embed this with this expression in this context, then if this program's reduced to an error, and the error blame label L, then this location, this L, must be associated with one of the runtime checks in the context and not in E, for any runtime error that you might have. So having this definition of robustness, so we say now the robust dynamic embedding means is stated as If you have a dynamic expression that is semantically typed to some type tau under some environment gamma, then the embedding of this expression into the Gradual language, and then the cast or ascription to some type tau is robust at gamma and tau, meaning that if you embed it in some arbitrary Gradual context, then and it fails, then the label associated with the error must be outside of this embedding and ascription. So in particular, we have a corollary, meaning that it states that if you have a semantically typed expression, dynamic expression, and you embed it into a statically typed context C, so a full static context C, then if you embed it into the Gradual language and you ascribe it to the static type tau, then this expression, this whole program cannot reduce to an error, because it will have to be some label in C, but if C doesn't have any cast, then it should be free of errors. So that's the criterion. I hope that this is the main point. I hope you understand it. So now that we established the criterion, there might be some questions. So for instance, is this criterion trivial? Is it easy to attain? Maybe every language satisfies this criterion. Is it realistic? Maybe not. Maybe it's something that is impossible to attain. Or maybe it's redundant with other properties that are other criterion in the literature. So we tried in the paper we tried to answer these questions. So the first one is it trivial? And therefore universally satisfied by every Gradual language? And the answer is no. So we are going to give you two examples. So let's suppose that we have a Gradual language that supports some types. And so suppose that you have a dynamic program, which is this function f, which takes a union as argument. And if it's an in-left or something, then it returns the same, the same sum. Otherwise, it's going to return an in-left of unit. So this function f is semantically typed to this type. So given a sum of 1 and Boolean, then it's going to return a sum of 1 and 1, a unit and unit. Sorry. And because this is exploiting like the fact that we have an in-left here. So if you believe me that, then the problem is that you cannot statically type this function f to this type, to the type that we just gave, because the first branch of the case has type unit plus Boolean, which is not equal to or consistent with unit plus unit. So what happens if we embed it into a Gradual language? So we take this function f, we embed it, and we ascribe this to its semantic type, the one there, and we apply this embedding and ascription to in-left of unit. Then, well, after a few reductions, we're going to have a unit cast to unit plus Boolean, cast to unknown, cast to unit. So what happened after this, it depends really on the semantics of the Gradual language. In some cases, for instance, if you have AGT semantics, you would get an error. And the error is going to be associated with label L, which is exactly the label that we have on the ascription of f prime, violating the criterion. So AGT by default violates this criterion. And there is another work that also implements sums, but that doesn't fail with this cast. It's more lazy. And if this program reduces to unit, then it's satisfying the criterion so far. We don't know if it's going to satisfy forever, but it's not violating because of this example. So this is like a counterexample that shows that if you have to pick the runtime semantics very careful to be able to satisfy this. So another example, if it's in the context of security types, where semantic typing is no longer like reduced to some value of that type, but in this case, semantic typing could mean some like richer properties, such as non-interference. And non-interference means public output, which is low, cannot depend on private input, meaning high. So we can say that this function that takes an argument and subtract this argument with itself is semantically typed to give me a private NAT and I give you a public NAT, because it is constant. Basically, it doesn't depend on the input, so it should be semantically typed to this type. And actually, you can prove it using logical relations. But you cannot statically type this expression, because binary operations on private expression yield private results. So, well, you cannot type it. But so once again, what happens if we embed it into a Gradual language where we only gradualize the security parts of the types? So in this case, this could be a type check in a Gradual language. And what happens if we apply this embedding and ascription to 42? Then this is going to reduce to 0, of course, because we have 42 minus 42. But then we're going to have a pending cast that is going to try to reduce a cast from a private number to unknown to a private, to a public number. And this is going to depend on the semantics. Once again, in some semantics, it will give you an error, and this error is going to be associated with the type, with the cast that we have here, violating the criterion, or some other like semantics do not fail and satisfy, for this case, the criterion. So once again, it depends on the semantic of the Gradual language. So basically, this means that maybe this is like unrealistic. Maybe this is just impossible to. It's an attainable ideal. So is it realistic or unattainable? Well, it can be proven, and we did it for a Gradual language that supports functions, that has functions, Boolean, sums, and pairs. So we start by defining our dynamic language, which is, instead of getting stuck, it throws errors. And also, it has labeled dynamic semantics to know. We put labels on every elimination place. And also, it has something special that I'm going to explain later, that it uses lazy downcast to function types, which is important. I will go back to this. And then we define the Gradual source language, which is comprised of static semantics and dynamic semantics with cast calculus. But instead of like making all the theory on this cast calculus, we instead provide alternative dynamic semantics where we elaborate Gradual languages into the dynamic language, thanks to getting errors instead of getting stuck. And we prove, of course, that these two dynamic semantics are equivalent. So everything that we did it by using the dynamic semantics. So we did this because our formal proof is based on a notion of semantic typing for the dynamic language. So how do we prove this? We start with semantic typing. This we did with using logical relations. And this means basically that the expression cannot error, and it's going to reduce to values of type tau. Then we make this relation binary, and we also relax it to allow failing, but on some set of pairs of labels, meaning that if the left expression fails, then the right expression should also fail, and the pair of labels should be on this permitted set of labels. And of course, we also extend this relation to talk about unknown types, because we are going to embed this into arbitrary Gradual context. So to prove this, we prove two main properties. The first one is giving a well-typed Gradual context. We prove that it is related with itself under the labels found in the context. And the second main property to prove the theorems, it's this one, that giving a semantically typed dynamic expression, then the embedding and ascription of this dynamic expression embedded back to the dynamic language is contextually equivalent to itself under the empty error label set, meaning that it cannot error, basically. So if you combine the two properties, we can derive the final. We can prove the criterion. So one important thing that I say I was going to mention is that we have to use lazy downcast on the runtime semantics. And to motivate this, suppose that we have this function f that takes a function h, and we apply h to any divergent expression. So in this case, any lambda that diverges. And then we apply the same function to unit. So of course, this function is going to be semantically typed to this type. You have to believe me. It's a very long type, but it is. So basically, because if h uses its argument, it's going to diverge. So it's going to be semantically typed to this type. Otherwise, it doesn't use its argument. So h of applied to unit is going to terminate to unit. So we can apply, we can embed this function. We could ascribe this function to its semantic type. And then we can apply it to this function that receives something. And it doesn't use the input and return just unit. And this is going to reduce after many steps to unit ascribed to the value unit, ascribed to the type unit, ascribed to a noun, ascribed to a function that to unit. So if we eagerly combine casts here, then we're going to violate the criterion. So what we basically do is we treat this lazily as a value, and only reduce this cast if we are going to apply this value to some other value. So this is something important. So, and the last question is RDE redundant to some other criteria? And as we don't have more time, we leave this for you to search in the paper. There's other things. We spoke more about other properties in the literature. We explain how we mechanize this in Rocq using iris. And we give more discussion on design choices and more cases of this criterion in other contexts. So thank you for your attention.
All right, I think we have time for maybe one or two questions. Yeah, go ahead, Phil. Or, right, there you go.
Thanks, that's really interesting work. As I recall, every other criterion in the literature is basically syntactic. Mm-hmm. It's not a semantic property. And you're dealing with the semantically well-typed property. So it can't be redundant to anything else in the literature. Did I understand that correctly?
Yes, that's right.
Right, so it's a trivial answer to that one.
Yeah.
But then could you go back to your first counterexample? I didn't quite follow that.
The sum types, this one?
Yeah.
Yeah.
So the orange there means statically typed or dynamically typed?
The orange is dynamically typed. So this is a dynamic expression.
Okay, and then you said what goes wrong is you cannot
statically type it.
You can't type it, but we don't care. It's dynamically typed.
Yeah, but we
so
want
what goes wrong?
But we know that it's semantically typed to this type, like with the type that is there. But if we assume that and we ascribe it to a static type in a gradual context, then this program is going to fail, and it's going to fail because of the cast that we added. So basically, it can fail because of the cast. So it's
so
not.
Wait, why does the unit there end up with type 1 plus b?
Sorry?
In the end, we can see this problem because unit has type 1 plus b, which it doesn't. Right? It's in left unit has type 1 plus b, but I don't see where the unit gets ascribed type 1 plus b.
No, the function is ascribed to a function that takes a 1 plus b.
Correct.
Yeah? Where does this come from?
Yeah. Why does p reduce to that?
Yeah, we can discuss this, but it's in the paper. We have the elaboration for this. But it's going to ascribe the input to 1 plus b, which is the expected input of f. And then this is going to, maybe it's in left. It's in left. Sorry, it's a typo. Sorry, it's in left of a unit. In left of unit should be, sorry.
I see, but then we try to ascribe it type 1.
Yeah, because we entered the first branch.
Offline.
Yeah, sorry. Yeah, it's a typo. Thank you.
You should move on to the next talk. Right. So, thank you.